And Alexander is going to talk about pushing neural networks to production on different platforms, common problems and possible solutions.
Thank you. Okay, hello everyone. In this talk I want to discuss some practical aspects that arise when you're trying to push your already trained model to the user. So it's common in production when you want your model to be applied somewhere and be of interest to the user. So let's review the typical pipeline that arises in deep learning. You typically train your model on GPU, and it's very powerful, have quite a lot of memory, and can compute crunch neural networks quite fast. And then, after you train your model, you want it to run on different devices, such as in the cloud, or maybe in mobile phones, or inside surveillance cameras, or even maybe in the browsers. So you want to touch all the users you can with your model. And there are several practical aspects that arise when you're trying to deliver your model to the users. And I will review not all of them, but some. The first one is the model size. And by meaning the model size, we can speak about two things. The model size of the model file. This is how many bytes our model should be if we want to transfer it to the user and make it work. And the second thing is the model size in the random access memory. So in some devices you have little memory, and if you want to run your big model that you trained on GPU, you should take some care of it. Model file size is especially interesting in mobile phones, for example, when you have your app, and if you want to embed a neural network inside, you don't want your app to grow 100 or 200 of megabytes. And the second common issue is the inference speed. So as I said, you typically train on GPU, and this is quite a fast device. And when you move to mobile phones or even CPUs, you see a big drop in inference speed, and sometimes you need to deal with it. And the last problem is battery consumption. So how hungry is your model for the battery of the device? And again, in mobile phones and embedded platforms is quite the issue with the neural networks. So in this talk I will cover two things, model file size and inference speed. And I'll review some recent papers that are quite easy to implement and may give you some possibilities to push your model to more devices. And let's begin. So the first problem is the model file size issue. And here is the motivation table. In this table you can see typical state-of-the-art neural network architectures with a number of parameters in it and the size of the model. And also the accuracy of these architectures on the ImageNet dataset. ImageNet is a state-of-the-art data set for measuring how good your image classifier is. So we can approximately split this table into two parts. The first part is the top one, and here we have big models that have a big model size, but also have a good accuracy on ImageNet. And the second part is the bottom one, is a model that's quite small. For example, tiny darknet is a very small model, but we also see that accuracy on ImageNet is not so good for these types of models. So what if we want it all? What if we want our model to be small and also accurate as models from the top part of the table? And there is several research papers that allow us, that answers this question positively and shows how we can compress our model by the factor of 30 or 50 without significant loss in accuracy. I will review two of them, and okay, let's begin. The first one is a paper from NVIDIA Stanford guys, and the idea here is quite simple. Let's try to find the weights in our neural network that is not important for the inference. So they do not influence the accuracy of the model if we delete them. Mathematically, this means that we zero them out and then use some compression algorithm that can compress sparse data, our sparse weight matrix efficiently. And the question here is what is the measure of importance of the weight? And we can measure importance of the weight, for example, using variation dropout, as Dmitry Vetrov already discussed. But here I want to review a more simple technique that also works quite well in practice. And the authors of the paper suggest to use weight absolute value as a measure of weight importance. And the iterative algorithm of compressing, pruning our network, zeroing out the weights, looks as following. At the beginning, we have already trained model that have a good accuracy on some data set of interest, and we want to compress as much, to zero out as much weights as possible on this model. So we begin with our initial weights matrix, and then find the weights in this matrix that have the smallest absolute values and zero them out. This is shown as green weights. After this, the accuracy on our target dataset has dropped because we modified already trained model, and we want our network to give a chance to adapt to these modifications. So we will retrain the remaining weights, the ones that we haven't zero out yet, and try to increase our accuracy to the previous level. And after this, we will repeat the same steps again. We will zero out weights that have the smallest value, retrain the network, and do it iteratively until we reach the desired compression rate of our network, or our accuracy is so low that we can't afford to zero out weights more. And these simple techniques give quite good compression rates already. So for typical neural network architectures, we can see like 10 times reduction in the model file size and with a little drop in accuracy. And it's also interesting to inspect these models, compressed models, layer-wise. And if we make a visualization of how many compressed weights we have in different layers of the network, we'll see that in convolutional layers we have most of the weights that is compressed to something like 60%, and the main compression is taking part in the fully connected layers where we have a lot of weights, and we can compress them to, and we can compress 96% of these weights. So the second paper I want to review is from the same authors, and they built on the idea of the first paper by additionally by additionally adding 2 steps after pruning. And the algorithm looks as following. We start from zeroing out the weights or pruning, and as I discussed before, then we use weight quantization and Huffman coding. I will go through these steps in detail on the following slides. So the pruning part is the same. After pruning, you get the model that has a lot of zero weights, and typically it's more than 90% of the weights of the model that are zeroed out. And then you start to quantize your network. Here the idea and the goal is simple. We know that a lot of compression algorithms benefit from having a lot of duplicates in the data, and here we want to increase the duplication number in our weights, and we'll do it by clustering the weights. We again start with the initial weights matrix and cluster the weights in the way that the similar weights are clustered together into the same cluster. Different clusters here are shown by different colors. Then we count the centroid for each cluster, and will replace all the weights from the cluster with its centroid. So after doing this, you can see that that's not working. You can see that we have a lot of duplicate weights in our network, and the weights from the same cluster are the same. And this is already good starting point to compress our weights matrix, because there are a lot of duplicate data, and if we run some state-of-the-art compression algorithm, we can expect good compression rates. But by doing this procedure, we have also lowered the accuracy of our model. So again, we will make network to adapt to this change by retraining it on our target data set, by fine-tuning only centroids of our clusters. And by doing this, we apply sharing restriction to the weights, so the weights from the same cluster change simultaneously and don't diverge from the same value. This step can allow us to get to the accuracy that we had before this procedure. And after this step, we have a weight matrix with a lot of duplicate values. So the last thing we want to do with it is to run some compression algorithm to get our compressed model. And there are a lot of possibilities we can choose. But if you look at the distribution of our weights in the weight matrix, we'll see that there are a lot of weights that encounter quite frequently, and a small number of weights that we can encounter rarely. And there is a encoding algorithm called the Huffman Coding that we can use here, because it assigns a small number of bits to the most frequent weights, to the most frequent values in our data, and more bits to the less frequent values. And this is a good fit for this unbalanced data distribution. And by doing so, we can, on the same models from the previous paper, we can expect additional almost 3 times gain in compression rates. So for the same models, we get 35 times and 49 times gain in compression. This is already quite okay for a lot of different devices you want to push your model in. So this was the first part. I hope that if you have some problems with the model size of your neural network, you can use these 2 simple techniques to reduce it and don't drop in accuracy. The second part is the inference speed. So the motivation table here is the following. We can compare different devices by the number of operations it can perform in 1 second. And if we compare GPU to server CPUs, desktop CPUs, or CPUs on the phones, we can see that GPU is on the top, and all other devices are quite slow comparing to your top GPU. And for example, if you take the recent iPhone 7 Plus, its processor can crunch the data to almost more than 100 times slower than your GPU you have trained on. So if you want to push your model to the iPhone, sometimes you need to take special steps to make it run faster. And I will discuss several approaches that you can use. The first solution here can be a specialized architecture. So instead of using some state-of-the-art network, you develop some additional architecture that is running faster on GPU and consequently on CPUs and other devices. And the seminal work here was done in a paper called Rethinking the Inception Architecture for Computer Vision by the guys from Google. And they proposed 3 ideas of how to modify a convolutional neural network to make it faster. And this is quite simple ideas. First one is you can replace your big convolutional filters with a stack of smaller ones. By doing this, you get the same receptive field in your filters, but this step can reduce computations by almost 30%. In this case, when we replace 5x5 convolution by the stack of 3x3 convolutions. The second step is similar, but you replace your squared filter with a stack of rectangular ones. It's also called separable filters, and you also get the same receptive field. The depth of the network is increased, but you can reduce the number of computation by the factor of by the 34% in this case. And the last step that was proposed is to inject additional bottleneck layer inside our network to reduce the number of channels in your filters. This bottleneck forces the network to propagate only the relevant information through it, and reduces the computational cost of your network by the factor of the number of reduced channels. So if you had 128 channels, as in this example, and inserted the reduction bottleneck represented as 1x1 convolution with 32 channels, you can get the reduction of almost 4 in the number of operations you should perform on your network. This is quite a big reduction. This is 3 simple steps that you can use when you design your network to get it perform more faster. And there was recently additional trick was proposed. It was proposed simultaneously in 3 papers. It seems like it's a good indicator of what that is really work, and it's called device convolution. Just to recap, the standard convolution is working is the following: you have your filter and you apply it to all the input channels of your image, and by doing this, you then sum up together the responses for all the filters, and it's your output. In device convolution, instead of applying your filter to all the channels of all the input channels, you apply each filter to each channel. So it's a massive reduction of computations. If you had 100 channels, 100 input channels, you get 100 inference improvements of the speed and the number of operations by using device convolution. But device convolution can be used alone because it does not combine information between the channels. So these 3 papers proposed to use the combination of device convolution and 1x1 convolution when can recombine the channels that we have. So the trick here is to replace standard 3x3 convolution by the stack of 3x3 device convolution, and additionally recombine the channels by 1x1 convolution. And in this example, this simple trick can reduce the number of operations by almost 9. It's also quite a big reduction. And the authors of one of the papers I review, called Mobile Nets, compared this architecture consisting of only device convolutions with standard architectures, and we can see that you can get almost 3 times reductions in the number of operations with the same accuracy on ImageNet. And the second solution I want to discuss is quantized networks. Quantized networks is we already seen that weights quantization can work when we want to compress the networks, but it turns out that we also can use quantized weights to increase the inference speed. And it works if our device has special instruction sets for multiplying quantized numbers. For example, in a typical situation, our weights are floating point numbers, 32 bits, and we have a lot of instructions to multiply 40 floating point numbers on the CPUs or GPUs, but there is also some instructions on CPUs and GPUs that can use, for example, 8-bit integer values and also multiply it and do it 4 times faster. And if we can quantize our weights and activations in the network to these 8-bit values, we can get the improvements in inference speed. So the first paper I want to review here is working with the network for speech recognition on CPUs. And the authors proposed to convert the activations in the network to 8-bit integers and the weight of the network to 8-bit signed integers. And also leave the biases as 32-bit integers, but it's just technical details because the instructions in the processor they used wanted these numbers as input. And this conversion was done by using linear linear conversion. So we take a maximum and minimum value of our weights and just map it linearly to the range that corresponds to 8-bit values. And by using special instructions that is highlighted on the slide, the authors was able to get almost 3 times reduction on the inference speed on Intel CPUs without loss in accuracy. And another possibility in networks quantization is to go to extreme and quantize the weights and the activations in the network to just 1 bit. So your weights and activations can take only 2 values, +1 or 1 or -1. And this type of techniques is also explored in the research. Here's the 2 papers, recent papers about this. And so it's like the same slide. You convert activations to +1 or -1, and also weights to +1 or -1, and use special instructions on the CPU or another processor that can multiply these bit vectors much faster than their floating point counterparts. In theory, we can get 30 times inference speed improvement by using quantized 1-bit vectors because instead of 32 bits we use just 1, and we can multiply 32 times more values in this case. And there was a question if it's really possible on current software, on current hardware and software, and the recent paper showed but it's really possible. If you quantize your network to just 1 bit, you can use the instruction sets from SSE4 on Intel's CPU and get more than 10 times improvement in inference speed compared to floating points. There is also the same instruction, for example, on ARM processors on mobile phones. So in theory, we can also expect to get the improvements on this type of processors. And I should put the warning here. Right now, the binary neural networks the accuracy of binary neural networks does not match the accuracy of their floating point counterparts. Here's the difference. But the good thing is that it's the active area of research, and the accuracy is improving quite rapidly. This is improvement in just 2 years. And I also want to add that in the near future, we should expect the explosion of specialized hardware for inferencing and training of neural networks. And a lot of silicon companies are working right now on the specialized chips. And this quantized and compressed network, I think they should be more relevant on this specialized hardware, because we just don't need 32 bits to represent our weights and activations in the networks. So that's the end of my talk. Thank you.
Do you have any questions to Alexander?
do anyone or you or someone else consider some exporting of trained neural network into a plain C function?
Sorry, can you repeat the last part?
Exporting a trained neural network into a plain C function that can be compiled with a compiler into a native code and then loaded as a dynamic module.
Yes.
And another related question, you have mentioned some low-level CPU operations. How are they implemented? Is it something like a just-in-time compilation or what else?
So starting from the last question, you just need to have this operation in the instruction set of the processor, so it should support it natively in hardware. Otherwise, you don't have any inference speed improvements because modern processors support floating point operations in hardware, and this is quite fast. So if it doesn't support your instructions in hardware, you typically lose to the floating point numbers. And asking the second question, we tried to write just plain C code and hope that compiler will understand how to translate it to the optimized instructions, but it doesn't typically work, and you should write the low-level intrinsics code by your hands to get the maximum performance.
Such a feature was implemented about 20 years ago in the Stuttgart Neural Network Simulator. It has implemented a function that generated a C code from his trained networks. Can you suggest, or are you aware of some modern packages or software packages that can do the same thing? Because that project is dead now.
Yeah, for example, MXNet is an open source framework for training neural networks. They have a possibility to convert your neural network to just plain C code and to make it easy to port it to different devices without dependencies. So MXNet is a good choice.
More questions?
Naturally, most of these approaches are focused on performance improvement on recognition operation of network. But if we are speaking about improvements or speeding of training, how does the last approach, XOR nets or quantized nets, influence on training performance?
Right now, it doesn't get any improvement in training, because in training you usually use floating point numbers and then just convert it, quantize it. But as I mentioned, we have special types of hardware. Especially in the future, there will be special types of hardware that will allow to use these quantized techniques also in the training and get inference and get speed ups here also. Sorry.
Including XOR nets as well, they are also trained as usual net, but then converted to bitwise operations. Are they?
I think any nets any neural networks can benefit from it.
Okay, so one last question.
My question is very simple. Have you tried to use these approaches in your work?
Yeah, we have tried compression, and it actually works. So it's easy to get 20 times compression without any loss in accuracy. We have also tried to implement neural networks on 4 mobile processors, and right now we almost tried floating point multiplications, but we also see that there is a possibility on mobile phones where we can use int8 instructions or even bitwise neural networks, but this one we haven't tried yet.
Okay, also we discussed some, in my opinion, technical approaches, but have you used in your work mathematical approaches for pruning neural networks?
We use extensively these modifications to the neural network architectures that I described, and it really works. So it's quite easy. You just design your network in a way that it's more computationally efficient than standard one. And yes, this one we use a lot.
Thank you.
Okay, let's thank all the speakers of this session. And so now it's a break, and at the same time there is a UC round. There are some posters, so we have around 15 posters here, and also a demo session behind you. So demo session is not huge, so please don't go everybody there at the same time, but please check it out. It has some interesting demos inside. And we will be waiting for you back at 3 o'clock.
Друзья, теперь я поговорю на русском немного.
У нас Russian a little bit right now. Our break will take 1.5 hours, and during these 1.5 hours, you will be able to see the poster sessions represented on the left side from me, and also in our audience next to me. The teams that have been working on these projects are going to tell you about them. And before we have started our second part, you can have lunch in Strelka bar, and here on the terrace, and the remaining lectures will start at 3 p.m. Thank you very much.
И, пожалуйста, если вы оставляете у себя
And please, if you keep the simultaneous translation devices, you can keep them with yourselves. But if you are leaving, please don't forget to return them to our volunteers, and then you'll be able to take them back if you will return. Thank you very much.